Okay.
Okay. Can you see my screen?
Yes, yes.
Okay. Okay, so thank you and hello to everybody. So I will present a brief overview of OASIS and how to couple different models with CROCO. So basically that's the work we are doing in CROCO since since a few years now. So and we recently we have redone all the scripts to couple CROCO to other models. So I will present you those new scripts, and then later this afternoon you will have a tutorial on that with Andres and Gildas. So I guess there is no need to present why do we want to couple, because thanks to Fabien and Swen, so there is many interaction. We just have a very brief overview on that. So there is a lot of interaction between the ocean, the atmosphere, and the waves. So this is an illustration here. So of course, heat flux with the solar radiation, the exchange of turbulent flux with sensible and latent heat fluxes, the exchanges of momentum through the wind and the wind stress, then all the wave effects. So the wave can act as an interface between the ocean and the atmosphere. It can filter the momentum, but it can also have direct influence on the currents, as Swan presented, through wave current interactions, long wave circulations. So as I said, the wave can be seen as a kind of interface between the ocean and the atmosphere. And actually, all the fluxes are estimated using parameterization and using this formula, actually. So basically, we need, sorry. Sorry for that. So basically, we need the sea surface temperature, of course, the currents and the winds, but actually, we will see, it has been shown, and we know that the transfer coefficient here, CH, CE, and CD, also depends in our bug formulations on the wave. So this is an illustration. It's very similar to that shown by Swen before. So this is a scatter plot of the 10-meter winds with the drag coefficient here. So we can see that it can have a large dependence on the wave. So in the classic simulations, in classic ocean simulations, it's not taken into account. It's barely taken into account, statistically at least, at most. And it will also depend, of course, of the age of the wave. So it depends, for example, here from 2002, whether the waves are old, are mature, or young. We won't have at all the same drag coefficient dependency on the winds. So there is also, besides the wave feedback, there is two main other feedbacks shown by Fabien before, the thermal feedback. So it can have a large influence on the atmosphere at the mesoscale, on the cloud cover, on the precipitations, and also on the winds through the wind magnitude, the divergence and the convergence on the wind curve. And it can have some effects on the ocean as a retroaction to the atmospheric alteration by the ocean. There is also the mechanical feedback. So basically the influence of the ocean currents on the atmosphere and the retroaction on the ocean. The main impact is the impact on the windward. So it also have an impact on the heat flux, but the driver is mainly in that case the exchange of momentum between the ocean and the atmosphere. So for example, here, this is a simulation season 80. This is a uniform wind blowing toward the south. And we estimate the windward as a cross product between the stress and the ocean currents. So on the right side, on the eddy here, we have a wind and a current in the same direction. So we have a positive windward, positive input of energy from the atmosphere to the ocean. On the other side of the eddy, that's the other way around. When we estimate the windward, we will have an opposite current to the wind, so that the scalar product is negative, and we have a sink of energy. But if we integrate over all the eddy, we will have a zero, basically no exchange of momentum, no net exchange of momentum between the eddy and the atmosphere. So it won't, if we don't consider the current feedback, we won't have any exchange of energy. In the case of a couple model here, I want to present here, but I will just focus on that one. We use the relative wind to the ocean currents, as shown by Fabien. And we have a reduction of the positive input of energy and an enhancement of the negative wind work. So that when we integrate the wind work over an AD, we have a sink of energy that induces a damping of the mesoscale activity. So basically, why do you want to couple? So there is strong two-way ocean atmosphere interactions at many scales. So from some mesoscale, and large scale during extreme events, of course, for example, during storms, there is a lot of exchange of heat and momentum between the ocean and the atmosphere. There is also a large wave generated. And in the tropic, where we know that it has been shown that we have large exchange of heat between the ocean and the atmosphere. There is also strong two interaction between a wave and currents. So in frontal regions, for example, where the currents can largely have an imprint on the waves, in coastal regions too, and in strong current regions, such as, for example, western boundary currents, Gulf Stream and Agulhas current, for example. So far, we are using bug formulation, but actually we are just using a kind of binary, but they are only valid under some conditions. In the bug formula we use in both ocean atmosphere coupled model and in a forced ocean model without waves, we consider that we have a moderate wind conditions, except for some formulation developed for high wind, but usually it is done, for example, the one CROCO, the COR1 is done for that. We have a fully developed waves. We are considering relatively large spatial scales. So, for example, when we are at some mesoscale, we are not really into that framework, and relatively low frequency, so order of a day. So basically, one of the questions that arises is what happens in other conditions. So, as I said before, there is processes we want to consider when we compare. So the SST feedback to heat fluxes, to latent and sensible fluxes, the current feedback to momentum fluxes and to heat fluxes too, actually. So the water flux, precipitation and evaporation, and the solar flux, of course, from the atmospheric model. Then there is also the loop between the wave and the atmosphere. So we will change the roughness evolution accordingly to the sea state. Can change also, the wind can also react to that. So we will have a change in both the wind stress, but also in the wind and the full planet boundary layer, and through the sea spray. And ocean waves, the loop ocean wave has potentially a lot of interactions. So that was presented by Swen before, so I won't be long here. So it can impact the sea level can impact on the waves. There is impact of the currents on wave evolutions. For example, it has been shown recently using satellite data and models that the Agulhas current have a large imprint on the waves. The wave-induced circulation, so stock drifts and transport, it can interact with the currents. The wave can also generate larger mixing due to wave breaking. So it can induce a deepening of the mixture depth, for example. It was shown by Kuvlar 2019. And surface and bottom streaming. So basically wave-induced thin viscous boundary layer. And mass flux used to wave roller, and then it's more coastal. So wave-induced pressure effect, additional diffusivity, and wave-induced setup that can be very, very important in the coastal regions. So this is the framework we are using. So usually in CROCO, so the ocean is CROCO here. In CROCO, we couple with WRF and sometimes with a meso NH, which is a French model. And waves is done through WaveWatch 3, but actually, if you would like to couple to another model, theoretically it's possible, but of course through some modifications in the other models. So the ocean exchange sends to the atmosphere the surface currents and the temperature. We can also play with that. We can, for example, send a smooth temperature if we want to isolate the mesoscale SST feedback, for example. We can also choose not to send the currents and have a thermal feedback only coupled simulation. And in return, the atmosphere will send to the ocean surface heat, momentum, and water fluxes. Then we can also couple to WaveWatch 3. So in that case, the CROCO will send to WaveWatch the currents and the SSH. And WaveWatch will send back to CROCO the significant wave height, mean period, mean directions, and the momentum flux, basically that is burned to generate the waves. So it will be removed to the momentum flux estimated by the atmosphere. And then we can add an additional loop, the feedback between waves and atmosphere, so WaveWatch 3 and WRF. In that case, WaveWatch in our current framework, WaveWatch will send to the atmosphere the Charnock parameter, and the atmosphere will send to WaveWatch the wind. So basically, with that framework, we can play as we want. If we want to couple only ocean to waves, we don't have to use an atmospheric model. But of course, in that case, we have to provide the wind to the ocean and to the wave, and then they will estimate themselves the fluxes. We can also couple only ocean to atmosphere. We can use only, if we want to neglect that loop, we can just remove it, and then we won't have the wave feedback to the ocean. So that can be very useful actually to disentangle the different effects and to isolate properly for example, the effect of the waves on the ocean. So all the coupling is done through OASIS MCT. So basically that's a coupler that will allow to interpolate, for example, the ocean grid to the atmospheric grid, to do some averaging, and it has many options, and it's very fast, so it's very efficient. So what is OASIS? So it's a coupler that is distributed by Surfax in France. It is based on 3 different libraries: the PISMA, coupling and time interpolation, the parallel exchange, MCT library, and the grid interpolation, script R library. Basically, we have to give a name list to configure the exchange and the transformation between the models. So you will have an example later. And it has a lot of advantages. First, it is already coupled to many models. For example, WRF, as I said, MesoNH, Arpège, Surfax, and LMDZ, that is another atmospheric model, WaveWatch, CROCO, Mars 3D, Nemo, and many others actually. And it can allow to have 2 ways of coupling, synchronous coupling. So basically, if we have 2 models, the 2 models will run at the same time. And asynchronous coupling, it's not very performant, so I won't advise to use it that way. So basically, for example, CROCO will run 1 hour, and then WRF will run 1 hour, and they will exchange at the end of this hour. But basically, they are waiting for each other. So we are using computational capabilities for nothing. And in any case, it's very easy to implement now because it has been done in many models. So there is a few calls to OASIS to add, and we have to compute to write a couple of new routines. So it's already done for WRF, CROCO, and WaveWatch. So basically, that is the OASIS architecture. So first, OASIS has to initialize. So there is two routines here. That one is for MPI. Then it will initialize the grid. So the grid's definition, for example, the CROCO grid and the WRF grid. And then it will compute that way some coupling weight, to do the interpolation, the online interpolation after. And the OASIS dev partition to define basically the partition of the models because WRF and CROCO will be parallelized. So we want to know that data is communicating with that one from the atmosphere. And then it's very easy. We just have to exchange variables through a put and through a get. So when we want to send a variable, for example, SST, we will put the SST toward the atmosphere and we will get the momentum flux from the atmosphere to the ocean. Then it's very easy. It's through the name couple, through the name list to tune the coupling frequency, to tune which model, which source we want to use, and to what model we want to send the variable. And we can easily change the transformation and the interpolation. For example, we can have a conservative interpolation or a linear interpolation or whatever. So basically in CROCO, this is what we have. There is 8 routines you can find in the Ocean folder in CROCO. So the first one is it's before the temporal loop. So it's where we will initialize OASIS and all the MPI stuff. Then the separate predefined, it's where we will do the domain partition, the definition. Basically, that's the initialization, the full initialization of the coupler, then of the grid here. And then we will have some put, get var, and get to have some, to send some variables from CROCO to OASIS, and that OASIS will send them to WARF or to WaveWatch 3, for example, and the other way around to receive some variables from WARF, for example. And this is MPI ROMs, so it should be, I guess it's CROCO now, actually. So basically, that's just a file with definitions of variables, parameters related to OASIS operations. So this is how it works, a schematic picture of how it works. So for example, here we have a wave model, WaveWatch 3 and CROCO here. So each model will start from a restart, for example, restart from wave and restart ocean. The time step of the waves is 90 seconds and the time step of the ocean is 180 seconds. And we want to couple every 360 seconds. So it means that every 6 minutes, we will have an exchange between the wave and the ocean. So we have to be very careful because, of course, the time step of the waves and of the ocean the coupling time step have to be proportional to both the time step of the wave and of the ocean. And basically, it's here every 6 minutes, we will exchange through OASIS feeds from CROCO and WaveWatch. So now we present the steps to set up a coupled simulation. So first, of course, we need to get the source code. So you have to be careful and you have to download the very last version of the code that will be released by today or tomorrow. But for the tutorial, we have the very last stable version of the code. Then you have to set up your configuration. So there is a simple script. You have to use the create config.bash with that option. Basically, that script will copy everything, all the sources, to a folder you have to choose, and then you can change whatever you want in that folder, but you won't touch anymore the source. Then you have to compile everything. So first compile OASIS, then compile your models in couple modes. So CROCO and WaveWatch, for example, or CROCO and WARF. So you want to make sure to use the OASIS libraries in both models. And then, of course, you want to compute all the pre-processing for your different models, the CROCO boundary condition, initial conditions, and, for example, the WARF boundary condition 2 and initial condition. Once everything is ready, then you can use the coupling toolbox to set up and run your coupled simulation. So I have an example here. So this is a suggested architecture, but of course you can do different if you want. So basically you want to have the CROCO model, OASIS, WARF, and WaveWatch. And here you can put all your configuration, for example, a Benguela configuration or a Chilean configuration. So this is for CROCO. So you can download it. So it won't be the version 1.0, but it will be the version 2. You want to download the CROCO model and the CROCO tools, or you can also use Git using that those lines. Same for OASIS. OASIS it can be downloaded through a Git too, through a Git clone command. WARF, to WARF, you want to use a version we have. Actually, we have a version which is a fork from the official WARF, but we have made some modifications. So you have to download it through that GitHub. And for same for WPS, but you have to download it from the official WRF model. But our WRF, of course, is fully compatible with the native WRF. We just have made some modifications for the coupling and other stuff. And for WaveWatch 3, you can directly download it from that Git. Everything is also specified in the CROCO documentation. Then you want to set up your configuration architecture and environments using the create config bash. And it's very useful to get the path of the environment variables of the script to facilitate the compilation and everything. So you want to edit it, and then inside you can say exactly what folder you want to use, which configuration, and everything. So then you have to compile, first you have to compile OASIS. So there is a doc on that. For the tutorial, you won't have to compile it because it's already compiled on the cluster, but usually it's very easy to compile, and there is many examples in OASIS and also in our script, even for classic clusters, so you shouldn't have any issues, but otherwise you can write us an email if you have some troubles in the compilation of OASIS. Same for WRF. So there is two options actually. You can compile it by yourself, a mano. So first, of course, you have to download the code, then you have to clean, and then you have to configure. In the configure step, it's where you will have to specify the kind of machine you are using, and then you have to do the compile em read, which is the classic way how to compile WRF. Otherwise, you can compile it with some helps we provide with our scripts. So you have some examples here, and you have I won't focus on that much because we did not present it before. But basically, you can find everything in the documentation and in the tutorial we made on the CROCO webpage. And you can also compile it directly using our script. So you have to go to your, after doing create config, you will have a folder name Benguela, for example, or Chile. And then using the path, you have to put all the paths here and the libraries you want to use. And then you just have to do that. And it should be able to compile the code. Same for WPS, but I will go to the next one. Then, of course, you want to compile CROCO, so that's the usual way, but you have to make sure that in your CPP-Def, you want to activate the coupling CPP-Def. So OA coupling is for ocean and atmosphere, and OW coupling is for ocean and wave. So if you want to couple both atmosphere and wave, you have to activate both options. We have also an option when you are running the script to submit a job, you can use the online compilation, and it will compile automatically the model following what you said in your environment path and the options you put in the files you have to modify it. So this is the pre-processing for CROCO, for WRF and WaveWatch. So for CROCO, that's the classic way. I guess you saw that maybe last week, or you already aware of that. So with CROCO, you can make easily a grid with make grid, modifying CROCO tools param.m. If you want to force simulation, you can have a climatological forcing using make forcing, and boundary condition using make bri, and initial condition using make ini. For WRF, you have to use WPS. You can refer also, we have some documentation on that on the website. And for WaveWatch, you have to, actually there is a tutorial, so you can just follow the official WaveWatch 3 pre-processing tutorial, or you can also create a grid from tools we provide. It's create grid from, so basically you have to have a CROCO grid, and then by doing make WaveWatch 3, etc., that guy here, it will automatically generate a WaveWatch grid from a CROCO grid. So that will be the very same grid, of course, with the same resolution and same domain. So then the next step. So this is represents the workflow and the philosophy of the new script we have. So you will use it this afternoon. So after doing create config, you have 3 main scripts to modify. Those ones here, the main-env script, where you have to set all the configuration, where is MPI, where are the netcdf libraries, where is OASIS, where we can find the WRF code compiled, the WaveWatch code compiled, the CROCO code compiled. Then with my name list, we can set the experiment. So which models we want to use. So we can activate with 0, 0, and 1, whether we want to use WaveWatch or WRF or just CROCO. The time stepping of each model. So there is a DT at, for example, for the time step of the atmosphere, DT OCE for the time step of the ocean, and the coupling time step too. So for example, if we don't use WaveWatch, you want to couple, for example, every hour. And you can also, you have to set it up in that file here. And that my job is basically it's to say the period you want to simulate, for example, from 2005 to 2006, month 1 to month 3, and then it will launch the jobs you want to, the period you want to simulate. And then you simply have to do a submit job, and it will submit everything using your configuration, and it should run, hopefully. So the coupling CROCO tool manage various aspects. So for example, the CROCO compilation, it can be online if needed, to get the model input files, preparing OASIS restart files. So you don't have to prepare any restart from OASIS, it will be done automatically. Edit the name list so we modify the name list from CROCO, WRF, and WaveWatch, and basically the script will automatically modify the name list to put the good number of, for example, of number of points in your grid in X direction and Y direction. In CROCO, the stretching parameters, the time steps, and all the many different options we set in the my name list script. Then it will launch the runs and putting output files somewhere, transfer it, for example, in a storage, and we can eventually loop for another job. So for example, we can just submit a job of 1 month, and once this job is done, automatically the next month will be submitted to the cluster. So basically, this is here an example of the workflow. So we have some definitions here on the top with my env path, the name list, the my job to set, for example, the period, the time setting, and then with the submit job, it will generate and submit a job to the cluster that we done all those steps here. So compilation, for example, getting the forcing file, getting the boundary file, editing the name lists, launch the runs, and handle the outputs and the files. So this is more or less the same. So here we have, after doing create configuration, we have here the different files we will have in our your config. It can be Chile, it can be Benguela, it can be whatever you want. So those are the files we want to modify, the 3 files here. Here, this is a script toolbox. So you may have to modify it if you want to do something specific, but basically here we have all the toolbox we use in our script to submit the job, to get the file, to move the files, to do everything basically. And here in those 4 folders here are important because it's where we have the input files, but the name list, not the netcdf files. So for example, in OASIS in, we will have the name list of OASIS. In CROCO in, we will have the kind of CROCO.in, but a generic one that will be automatically modified by the script. and same for WaveWatch and WRF. In jobs view experience, you will have all the log file in that directory. Then we split actually in two, because we are used for that kind of configuration. Usually you use a cluster, so and you cannot put everything on your home, otherwise you will just saturate the home space. So usually we put all the files, the netcdf files, on a work dir, Scratch or TMPD or whatever. And with create config, automatically it will create a kind of mirror of that folder here, but here it's where we put all the netcdf files, the boundary conditions, the initial conditions, and everything. And it's where overall we will run the simulation. So we run all the simulation in Benguela, for example, execute. So it's actually where the run will be done. Then we will move all the outputs in that directory, and all the restarts that will be used for the next month, for example, in that directory here in restarts. So you can find more details here. We have a new doc on those scripts, and Andres and Gildas will assist you later this afternoon to use the script to make couple configurations, so CROCO WaveWatch and CROCO WRF. So you may have some error, of course. So in that case, there is some files you really want to check. So in that case, you have to come back to the home directory and to the jobs your experience. Basically, it's where we put all the log file. So usually in a cluster, you will have an output job file, name this way using our scripts. Then you can also check the croco.log files, the WRF error files, and the log file from WaveWatch in the folder where you execute the models. And there is also all the OASIS log file that can be useful to check. Typical issues usually we have or we had. A classic one is an absence of the file. So files are not found. So you want to check the file names, basically, if they are done exactly as we expect to have them. For example, we want to have a CROCO underscore BRY underscore soda, for example, with year and months. So it's everything is specified in the documentation. Sometimes you can have inconsistencies between the dimensions of the files. So basically, in that case, you want to double check you are using the good grid from WRF, from CROCO or WaveWatch. And sometimes we can have inconsistencies in the OASIS name list. So in that case, we want to check whether we are exchanging the actual variables we want to exchange. For example, SST, currents, wind. And if we have a blow up in the model, in that case, we want to check the CFL. We can have a very large speed. And in that case, it's very easy. That the classic way in CROCO, you have to decrease the model time step, and you want to make sure that the coupling time step is still proportional to the CROCO time step. So you can have, you will find some example on the CROCO official website. And I put here some reference. And so later this afternoon, you will use the script, thanks to Andres and Gildas. Thank you.
Thank you, Lionel. Questions?
I saw we had questions on the chat, but Sven already responded to it, right? I have the impression. Yeah. So yes, basically that's the last Word version or one of the last, but using the Git, the GitHub stuff, we can easily have an update to the very last version if we want. But you really want to use the version we provide to have the good coupling files in the model. Soon, it's already planned to send all the routine to the official WRF, but well, it has to be done.
I think mostly for the atmosphere wave coupling, no?
Yes, for that, but also for the name. Actually, we changed the name of the exchange of the variable that are exchanged between the ocean and the atmosphere.
Okay.
And also, yes, actually, I did not present it here, but we also have a lot of modification for XIOS. So it's an IO server, but you won't use it here. But basically there is a 4 main modifications: wave coupling, coupling generally speaking, though some of them are already available in WRF, and XIOS, and so some stuff for the droplet in WRF, but it's secondary.
Okay, great. More questions? Well, if not, we'll stop here and we will see each other 2 hours, 20 minutes for the tutorial. We will do we'll see the framework for modeling, where we will run CROCO and CROCO on Waywatch, CROCO with WRF, and on the 3 of them. In the Benguela case, to create a new domain, to do it for your own domain, that's much more complex. So, but let's start understanding where the thing should be.